going to do a deep dive into BIP324. We're going to look at how the protocol actually works and appreciate the engineering details behind it. And that's my goal by the end of the talk, that you all appreciate the engineering details behind it as much as I do, if not more. I see. Okay. Yeah, thanks. Yeah, so quick intro about myself, since my first time this part of the world. I go by Stratospher on the internet. I'm a Bitcoin co-contributor. I work on P2P network and also a few things in libsecp. I also do Potions at Bitshala, it's a community to onboard Bitcoin devs in India. We run a lot of experiments, so that's why I called it Potions. So this is the Bitcoin P2P network. All the nodes you see, they are full nodes, and they all need to talk to each other because it's a gossip network, and that's how nodes communicate with each other. They do so by exchanging messages to each other, P2P network messages. There are all kinds of P2P network messages you can send to each other, like version, if you want to, that's the first P2P message you send if you want to connect to a node. Ping, if you want to ask the node, are you still connected? You send the ping message. Get adder, you send that message to the other node. If you want to get a list of all the IP addresses of possible peers you could connect to. So this is how information flows within the P2P network. However, there are some problems with it. As it was before V26, the thing is that it's self-revealing. So all network messages, they are exchanged in this same format. They will always have 4 bytes network magic. Then there will be always a 12 bytes command and then the payload. So if you're sending a version message, it would be VERSION and everything else padded with zeros. So anyone with access to this packets, they can just see the first 4 bytes network magic. Network magic bytes is what identifies a network. So Bitcoin mainnet would have something different from testnet, so on. If you take something like Wireshark, they decode the packets, and you can see that Bitcoin packet, exactly what the contents of the version packet were. The other problem with this is that it's unencrypted. So anyone with who can see the network topology, like internet service providers or anyone with access to these packets, they can know who's talking with whom and infer where the messages originated from. So supposing you broadcast a transaction, they would be able to know where the transaction was first broadcast from and infer who's transacting with whom. Or they'd know where a block came from and infer where the miners in the network are. And that's pretty dangerous information for partition attacks and things like that. So we want to avoid those kind of leaks. And another thing is that it's unauthenticated. So you can kind of interpret authentication in 2 different ways. One interpretation of authentication is with respect to identity, and the other is with the respect to the network message itself. So supposing Alice sends a network message to Bob. Does Bob want to know that the network message was sent from Alice herself, Alice the person? So that kind of brings the concept of identity into the Bitcoin network. And that's controversial, and that's not something we want widely used. Oh. Okay. Yeah, we don't want it. So it's always restricted to really specific scenarios, the same nodes operator or something like that. So so authentication is always restricted. That kind of authentication is always restricted to very specific scenarios. The other interpretation of authentication is the network message itself. When Bob received the message, Bob should have no idea who the packet is from. It doesn't matter. But Bob should know that the packet hasn't been tampered with, because if it's tampered with, it's not good. Right now, if the message is sent before V26, you could modify service flags on the fly, and no one would be able to know it. So yeah, this is what BIP324 does. So I mentioned earlier that if there are two nodes, how they establish communication with each other is by sending the version message first. It's called the version handshake. So, like before BIP324, I'm going to call it V1, and after BIP324, I'm going to call it V2. So I'll be using that terminology, so don't get confused. So in V1, how nodes communicate with each other. How they do that is by sending a version message first. The other node responds back with verac and its version. That is called a version handshake. In V2, that is not the first message which is sent between nodes. They do a special kind of V2 handshake, ECDH based. So I'm just going to call it V2 handshake. So that is how two nodes communicate with each other in V2. So that's one difference. And the second thing is that, before BIP324, that's in V1, everything is in plain text. And after BIP324 V2, it's all pseudo-random encrypted bytes. And then there's this question, why not just use Tor? Because Tor, when you send packets over Tor, Tor does its own internal encryption. And yeah. So the thing is that we would want a solution which works everywhere. It's bad for the Bitcoin P2P network if a huge portion of the nodes just migrate to Tor. Tor has huge latency, cheaper network partition attacks. It's very simple to set up a Tor node. Your Tor identity is just a public key. It's very easy to spin it up. It's much harder to get IPv4, IPv6 addresses, right? So, yeah. So we want a solution which works everywhere, and it should be available to common people who want to use it. So these are kind of the goals of BIP324. We want confidentiality against passive attacks. No internet service provider or passive observer should be able to tell what the contents of the message are. So now that people can't be passive, they're forced to become active. So if you want to attack, if you want those messages, you're forced to run a Bitcoin node to get those messages. So you've essentially raised the cost of attacks. And then, yeah, the byte stream now looks pseudo-random, which is good, and it's also shapeable. So you can do stuff to make it resistant to traffic analysis. So that's very cool. We also want forward secrecy. That is, supposing by any chance if the attacker gets to know the latest key, they should be able to, they should not be able to decrypt the entire historical set of messages which were exchanged between the two nodes. Maybe only a fixed set of messages should they be able to ever decrypt. So that's what's called forward secrecy. Upgradability, if we ever want an upgrade path, if in future we want authentication or post-quantum crypto. So at the protocol layer, we need an upgradability path. So that's something else which 324 does. Compatibility. The V2 nodes should be able to talk with V1 nodes. V1 nodes are the unencrypted one, which I mentioned. And low overhead. We want all these features, but there shouldn't be a significant increase in the usage of compute or bandwidth. Yeah, so this is very quick. Yeah, so we're just going to look at the basic components very quick and then just design the handshake ourselves. Everyone, I think, here knows what encryption and decryption is. Basically, the people who, so if there are two nodes, the initiator and responder, if they send things in order to be able to encrypt and decrypt the same message, both of them will need the same keys. So that's the essential point I was trying to make. And then I mentioned the version handshake before. In V1, that is what the Bitcoin protocol says. How two nodes start the communication with each other is by sending this version and receiving the verac message. So in V2, we would want encryption even before this version handshake is done. So yeah, that's another point. And ECDH, that is how two people establish secret over insecure channel. So essentially there's user A and user B. Each of them will have its own private key and its own public key. So it's possible for user A and user B to arrive at the same shared secret. If user A has a public key, it multiplies it with the other person. I multiply my private key with the other party's public key and I get a shared secret. And this shared secret will be only known by the two of us and no one else in the network will be able to know this shared secret. Yeah, so this kind of by this time, you can kind of imagine what the, how you can design the handshake, right? There are two nodes running in order to encrypt and decrypt, they need the same same keys in order to be able to encrypt and decrypt. So they do an ECDH, and they get the same shared secrets, and they derive keys from it, and then they use these keys to encrypt and decrypt all the other messages which happen in the Bitcoin protocol, starting from the version handshake and anything else in the future. So yeah, but then there's another problem. Like we do want to make like the entire byte stream like traffic shapeable, and like no one should be able to detect patterns in it. The problem is that like ECDH starts by sending a public key. Public key has a very detectable pattern. Like they all if like it's like public keys are basically points on an elliptic curve. So they will always satisfy the equation y square is x cubed plus 7 mod p. So any passive observer, like internet service providers or anyone, if they do traffic analysis on it, they will be able to know that a public key is being transmitted over the network rather than like a random byte stream. So we want to make this public key look like a uniform random byte stream. And for that, there's an algorithm called alligator swift. So we use this algorithm in order to make the elliptic curve point look like a uniformly random byte string. So I will call this alligator swift sometimes L swift and things like that. So yeah, just to make sure we're on the same page. Yeah, and so now we can like come up with a very naive design. There's node 1 and there's node 2. So you need to do ECDH, that is basically exchange public keys. So node 1 sends its public key to node 2, and node 2 sends its public key, that's L swift y, to node 1. And now both of them have their own public keys. They can do ECDH. Then they can derive keys in order to encrypt and decrypt the messages. So that's ECDH. You also send a transport version so that there's a future upgradability path. So that's why we send a transport version. And node 1 also sends its transport version to node 2. So yeah, so that's like a very naive design, but we don't do it. Any ideas why? Like, sorry? Yeah, it's exactly. It's a detectable. Oh, yeah, it's a detectable pattern. Like, it's always node 1 will always send 64 bytes first to node 2, and then node 2 will always respond back only after exact 64 bytes with another set of fixed bytes. It's 64 plus the size of the transport version packet. So anyone can see, like always 64 bytes sent first, then 64 plus that X bytes sent first. So that's bad. We don't want to do that. We want it. We want the traffic to be shapeable. So we also send pseudo-random garbage bytes. Like that's next approach. So like node 1 sends 64 bytes, and it also sends a lot of pseudo-random garbage to node 2. And node 2 will also respond back with the alligator swift and a lot of garbage. And then we also need to know when this garbage terminates, right? So for that, there's a garbage terminator. And that terminator can also be derived from the ECDH secret we talked about. Like the shared secrets, which only node 1 and node 2 knows. So they will be able to derive the keys to encrypt, decrypt, and also the shared, and also the garbage terminator. So node 1 will know when the garbage from node 2 terminates. And then everything else is the same. Like you still send the transport version, and node 1 also responds back with the terminator and yeah, the transport version. Yeah, but this is still bad. Any idea why? It's again kind of related to like, in the beginning, node 1 would always send 64 bytes, and then node 2 will respond back only after it received 64 bytes. Now, node 1 sends 64 plus the pseudo-random garbage bytes. So it's always like you're sending greater than or equal to 64 bytes, and the response comes back only after greater than or equal to 64 bytes. So best case scenario would be like, you don't need to even wait for 64 bytes. Like when you send bytes, immediately the response should be like received back. You shouldn't need to wait for 64 bytes to be sent from node 1 to node 2 for the response from node 2 to come back, right? So that's like the design we do. So then the question is, how does node 2 know the other node is running BIP324 or not running BIP324? So there's actually no way to know unless you actually receive the network messages. So node 2 would, if node 1 is a V1 node, it would send the version message which I talked about in the very beginning first. And the version message, they always have like the same fixed format, right? So it will always start with magic bytes, then VERSION, and then lots of zeros. So that 16 bytes is always fixed. So what node 2 does is, when it receives the alligator swift bytes, it checks whether there's a mismatch from that first 16 bytes of the network magic and the command VERSION. So when the first mismatch happens, it immediately responds back with the alligator swift byte. So most cases, the mismatch would happen in the very first byte. So you immediately get a response back from the other node after the first byte itself. That's what happens in most scenarios. So yeah, that's the design. And then, yeah, we also have a packet encryption cipher. So now all the things are encrypted and they have a new packet design. So there's the length first, then the contents, and then the MAC tag to authenticate the network messages. And yeah, so also the contents also has this header. It's a 1 byte thing. So if you set it, the whole message will be ignored. So like I could send you a network message, and if I set it 1, like if I set the header byte, that means that you should ignore the entire message I sent you. So this is helpful in traffic shapeability. Like I could just send a lot of fake decoy packets to fool the ISP or like anyone doing traffic analysis. So yeah, in very brief, like I talked about the V2 handshake happening first, and then they get the keys to encrypt and decrypt, and then all the P2P messages get exchanged between the nodes, and yeah, they send in a new encrypted format now. So that's what BIP324 essentially does. And yeah, we can do more, like this LSwift-based ECDH, which I talked about. It can be done in any kind of protocol where you do public key exchange, like Stratum V2, like it has recently used this LSwift-based ECDH. It's added this as one of the options to do the ECDH. Maybe you could even have it in noise library soon. Yeah, and then yeah, the stack had recently made this proxy to for light clients in order to be able to talk V2. Like we have V2 from version 26. It's an experimental feature. From version 27, we've been shipping it default on. So yeah, so you can so for light clients, you can use this proxy, which is completely experimental in Python, but it works. Like it's just like someone is writing it in Rust for production use maybe, but yeah, it's still a prototyping phase. Yeah, essentially you can run a proxy which would capture all the V1 traffic, and the proxy would do the version handshake, would do the initial V2 handshake with the remote node and make it all V2 traffic. And it's V2 traffic which is being broadcasted over the public internet. So no one will be able to understand, see the contents of the message. Yeah, and then there's like a replit. If anyone wants to play around with this proxy, like I've essentially put the light client code and also the proxy code, so you can literally run it on the REPL. And yeah, these are just ideas. You can do more stuff to there's a lot of cool traffic shaping stuff which can be done now because of the LSwift handshake and all that header byte thing which you can do to do traffic shaping. So this is just one idea for parroting other protocols. There's a there's a special property of LSwift using which you can fix the first 32 bytes and still the mapping from the mapping from the LSwift, the mapping is still valid from the public key to the LSwift bytes. Even if you fix the first 32 bytes, and you could maybe fix the bytes for something like TLS or something and use it to parrot other protocols. Yeah, and then you can also run maybe a monitoring dashboard. Yeah, like Vertu had lately published, like I think yesterday he did a tweet, and apparently 1 in 10 Bitcoin nodes run V2 now. Yeah, that's it. Thank you. Okay. Questions? Yeah. We're still we do still suffer from timing analysis and things like that. BIP324 is not like a perfect solution. Like, oh yeah. So he was asking like whether BIP324 would like protect you against timing analysis. Like for example, when a new block comes in via the P2P network, there would be a sudden spike in the traffic when you receive the block. So still like clever people doing the traffic analysis, they'd still be able to know that like you're running a Bitcoin node. So it doesn't protect you from those kind of attacks. Anything else? Yeah. If things apart from Bitcoin, like yeah, have this. Uh, you mean the L-Swift based ECDH? Yeah. Uh, so, mm, so you're like kind of talking about like hiding traffic patterns, but not the L-Swift based one. Anything. Yeah. Ah. Yeah. Makes sense. Yeah. So, yeah, the question was about like BIP324, the nodes they communicate in pseudo random bytes with each other, and if there's any other protocol which does this same kind of thing. From what I know, like one of the problems with running BIP324 is that it's really good pseudo randomness, and like no other protocol actually does this level of good pseudo random bytes. So that's so thing you could do is like maybe like run like HTTP protocol wrappers or something like that. But ideally, the entire community upgrades. Like, I don't know. It's a good question. Hmm. Yeah, I guess one thing you could do is like, yeah, the question was about like when a new block comes, you get lots of traffic spikes. Can you can you make the traffic look like something else? So we could use the header bytes, like which I talked about. Like if you set it, the packet will be ignored. So like you could run a client which sends lots of these fake things and make the people think, yeah, it's decoy traffic.
And the standard configuration, if I install the 27, does it send any garbage traffic or how much? Like,
yeah, it does send, like it's 4096 bytes of garbage at max, which can be sent. So it could be any, like you choose a random number between that and you send pseudo random garbage up to 4096 bytes.
like the node does that automatically?
Yeah, the node does it automatically. But we don't have support for the decoy traffic, like the setting the header byte to 1, like that is not done. So if you want to do that, you'd have to like explicitly configure the node. I guess that's it. That's it. Yeah. Thank you.